Now let's look at some definitions. What is the average, or otherwise called as a mean? You sum the total number of observables, observations for a particular parameter. For example, a score, right? A score on a test. You divide it by that particular number, and you get what is called the average. Okay, and the bar is a average notation. So the population mean of a population, that is, now we're looking at larger numbers, is a number mu, the Greek for m, defined by the formula mu is equal to the sum over the population. So that is a definition of a mean. Now let's look at a median. A median is, and there could be a better representation of this. This is a median, has really a tilde representation on top of it, just like the mean has a bar. So the sample median of a set of a sample data for which there are an odd number of measurements is the middlemost measurement when the data are arranged in numerical order. So if you have a set of data and you arrange them in ascending or descending order, the middlemost number, the middlemost measurement, the middlemost numerical observation is the median. Okay, and it is different from the mean depending upon how your data is collected or the nature of your data. If you have an even number of measurements or observables, then the middlemost two numbers are averaged, and that is what gives you the mean. Okay, so for an odd number, it's easy. The middle number gives you the median, and the odd number is and if it's an even number of terms, then the average of the even number is taken. Okay, so this is the median, the middlemost term, not necessarily the average, and we'll look at that. So again, the x with the bar is the mean, the x with a tilde is a median. Now, in a bell curve representation, for example, again, we don't worry about what the distribution is, we just look for the middlemost number. So the middlemost number is the median, and the mean is there. Now, in this particular case, you'll see that the median equals the mean. There is another case where the median equals the mean, and that is another characteristic like this. On the other hand, if you have, again, remember, we don't care about the distribution. Let's say I have two measurements. One is, three measurements, and something measures as 10, something measures as 15, and the same thing measures as 100. So the average of 10, 15, and 100 should be somewhere in the 50s, okay? But the mean is still going to be 15. And so in this case, you see this distribution where the median is still the middlemost number. But the mean, because there's a greater frequency of numbers in this range, you're going to have the mean move to this side. And on the other hand, if you have a characteristic like this, where most of the distribution is centered around here, the mean is going to be towards this, but the median doesn't care. It doesn't care about the nature of the distribution. It just says, I'm going to find the middlemost number. Okay, that's what you see here. The mode is the third of the M's, mean, median, and mode. And mode is basically the thing with the highest frequency. Okay, again, the mode doesn't concern ourselves with the mean or the median. It is the highest frequency. And if you look at this particular distribution, it is here where you have the frequency that is the highest. So again, remember this. Remember, these curves are just histograms which go from discrete to continuous because we are dealing with really large samples, right? Look, with small samples, you could just say, okay, I can measure this by hand, right? But the statistics is really important when it comes to large samples. And that's why biostatistics came about. It was always there, but it came about or grew in prominence in terms of applicability in the biosciences because of next generation sequencing, high throughput methodologies like microarrays, etc. Now let's think in terms of the variability. Two data sets that are collected here. What do I mean by variability? How are these data different, right? Now, if you look at it from kind of a bird's eye view, you say, well, okay, I've got two sets of measurements, probably of the same thing. They are, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 measurements, okay? And the numbers seem to be, well, they're kind of the same, right? 40s, 30s, but there's something going on here, and let's take a look at that. If you look at the distribution of this, you realize that numbers are kind of all close together in data set 1. Okay, so for example, the smallest number in this is 38, and the biggest number in this is 43. So if you do a distribution here, you'll see that they're all kind of clustered together. Okay, they're clustered together. This is a very precise data. Now, on the other hand, from a bird's eye view, you say, yeah, there are a bunch of numbers in the 30s and the 40s. Well, not necessarily, right? So, for example, you see, while here the lowest number was a 38 and the highest number was a 43, here the lowest number is a 33 and the highest number is a 47. So look, so my point is the data, when you just look at it, doesn't feel like it's telling you much, but if you look at the frequency distribution, right, you'll realize that this data is clumped together, very precise, okay, which means the deviations are not much, whereas here you see the deviations, right? So whatever the mean is, looks like things are on either side of the mean, they're kind of really, really spread out, okay? And that is one of the reasons why data presentation is really important. What is the range? Now here's a definition that is important. So a range of a data set is essentially the difference between the largest and the smallest number. So for data set 1, you see the range is going to be small because everything is just clumped together, and the range is going to be large. So what are the numbers of what are the measurements here? The lowest number is 38, the highest number is 43, so the range here is 5, and you go from 47 to 33, the range here is 14, okay? And so again, numbers that look the same, but when you plot a frequency plot, you'll realize that there is variability in the data. That's the difference in the different data. Now it's important. Very often, it's we talk about definitions of accuracy and precision, and we say precise when we mean accurate. We say accurate when we mean precise. So accuracy is the closeness of a measurement to the true or accepted value. And what is precision is closeness to the mean, okay? Now, as we take these numbers to larger numbers, you see that we have what is called the population variance and the population standard deviation. So the variance is defined as, so you take the mean, you take the value, subtract the mean, and we don't worry whether we don't worry about the deviation because this is squared anyway, so we don't worry whether it's greater than or less than. But what is the deviation? The deviation is how different is your measurement from the mean, okay? And then you divide it by n, which is the total population, and you get sigma squared, and that's called the population variance. And you can also take the population standard deviation, okay? And these words, sigma squared, which is the conventional term used for variance, and sigma, which is the conventionally used term for standard deviation. A sample variation for n sample data for a small data set is defined by the formula n-1. When we talk about degrees of freedom, that's what we're going to look at, n-1 degrees of freedom. Okay. Now, it's important to begin to understand variance and standard deviation. So let's say here is where we have a distribution. Okay, here is where we have a distribution, and this is very important. So if you have the mean here, which is mu, and let's say you calculate the standard deviations, right? So one standard deviation, so mu, so it's like this is the standard deviation on the positive side and on the negative side. Okay, that's the standard deviation. And if you have what I call two standard, you take the standard deviation, you multiply it by 2, and you say, well, 2 standard deviations are here, 3 standard deviations are here. What does that mean? It means that a standard deviation about a mean, if you say that my results, let's say I'm calculating, I have 200 students and they take an exam, and 200 students, you get a certain average. And if I say somebody's score is 3 standard deviations beyond the mean, it means I find the mean. Let's say the mean is 50, and I calculate the standard deviation, and the standard deviation is 10. So you would say, well, my mean is 50 in a score of 100, And I say that the person who gets an A grade is the student who has 3 standard deviations or 4 standard deviations beyond the mean. So if I calculate a standard deviation and it's 10, so I would say that my first standard deviation is the number of people who are between 40 and 60, right? 50 is the average, so 40 and 60. And the second standard deviation is somebody who has between 30 and 70 and 20 and 80. And I say the fourth standard deviation should be anybody who gets over a 90 gets an A. And on the other hand, I could say if you are within a negative 3 standard deviations, it's an F. Okay, and so somebody who gets lower than this score gets an F. And that's why we talk about standard deviations.